I welcome you to this lecture. Last time we stopped at what we call the inverse of a matrix when we are using the determinant. If you recall very well, we talked about some few things. That to get the inverse of a given matrix, we shall be using this formula 1 over determinant of A times what we call the adjunct of that given matrix A. Now, last time we looked at how best we can get the cofactor matrix, and we said that the adjunct of any given matrix is same as taking the transpose of the cofactor matrix. And we as well looked at how best we can obtain the determinant of a given matrix. It can be a 2 by 2 matrix, it can be a 3 by 3, and we also looked at the matrices that have the order which is greater than or equal to 3. So all this we looked at that when we are meeting physically during our physical classes. But today we want to look at something new on top of where we stopped. In the previous lectures, we looked at what we call the inverse of a matrix. And if we now know how to get the inverse of a matrix, then it will be easier for us to deal with what we call the systems of equations. So to look at the system of equations, we shall use what we call the inverse. So we looked at the inverse by basically looking at an algorithm where if you augment your matrix together with an identity matrix, the corresponding identity matrix, then you use row operations until you obtain the identity matrix. Then here what you will have will be your A inverse. We looked at that algorithm of how best we can obtain the inverse of a given matrix A by augmenting it together with an identity matrix, and we use row operations until we are able to come up with the identity, then a inverse expression. We also looked at another one where basically we talked about the cofactors. That is, by using the cofactor matrix, if you recall very well, we talked about getting the inverse by basically looking at 1 over determinant of a matrix times the adjoint of that given matrix A. But if you also recall very well, we said that the adjoint or the adjunct of a matrix is obtained by taking the transpose of the cofactor matrix. So we looked at all these procedures here of how best we can obtain the inverse of a given matrix. So for today, we want to look at what we call the systems of equations. And we shall be saying for a system of equations, if you have a square system of equations, that is the equations that have the same number of equations as variables. So we shall use the theorem that we shall have below here. And the theorem of the systems of equations with unique equations says that if you have a matrix A which is an invertible matrix, or in other words, A is a matrix whose inverse can be obtained, then we can easily solve systems of linear equations which are of the form AX is equal to B. A is simply representing the matrix which is the coefficient matrix. Then this one X is representing the matrix that will be containing only the variables. Then we have got B, which is representing the matrix that will basically be containing what we call the constant terms. So if you have such systems here, which can be placed in the form AX equaling to B, then we shall say that this system has a unique solution if we have X equaling to A inverse minus B. So this will be the solution. In other words, if you have x1, x2, so this will be the variables that are within this matrix. So they are equivalent to having A inverse. So you will first of all obtain the inverse of this A, then you multiply it together with the constant what? With the constant terms. So you are having your A inverse here, you are multiplying it together with the B. B is the matrix of the constant terms. So you will also have it there. So what you get here will be the corresponding values of x1 and x2. So the system can have x1, x2, x3. The system can have x1, x2, x3, x4, all that one there. But basically, we shall use what we call ax equaling to b. We first place it in this form. Then after placing it in this form, then we shall now have what we call the solution as A inverse times B. So the most important part here is, after putting it in this form of AX equaling to B, then you will need to use any of the above procedures for finding the inverse of a matrix, and you obtain the inverse of A. After obtaining the inverse of A, then to get the solution, you will simply get that inverse, you multiply it with B. So let us look at the proof of saying that our solution will be x equaling to A inverse of B. So if you have your AX, if you have your AX, if you have your AX is equal to B, if A is non-singular, in other words, A is invertible, which means that A inverse exists. So if A inverse exists, then we can say that A inverse, we can multiply it on both sides, will be equal to A inverse times of B. But what is A inverse times A? We know this because A inverse times A is same as an identity matrix, is equal to A inverse of B. So you know this is the identity matrix, that is IX, which is same as A inverse of B. So in other words, X will simply be same as getting the inverse matrix, multiplying it with B, which is the matrix of the constant terms in the equation that we shall be having. So to understand this, we shall look at some few examples. So let us look at some few examples, then we shall be able to appreciate how best we can solve a system of equations using what we call inverse of a matrix. So we want to solve a few numbers here to understand very well how best we can use the inverse to solve a system of equations. So we shall begin with part A. So the question says that use an inverse matrix to solve each of these systems. So we are having this equation, we are having three equations here. So within these three equations, we can place them in a matrix form. So in matrix form, this will be 2, this will be 3, this will be 1. So this will give us 3, the next equation 3, 1. We are taking the coefficients of these equations here. Then the next will be 2, this 2, then this 4, then this 1. That is what we are having. So this one here is into, so this one is into x, y, and z. And this is same as equal to. So we are having -1, we are having 1 here, then the next one is -2. So we are expressing these equations in a matrix form. So doing that, we can easily now see that this is in position for A, this is in position for X, and this is in position for B. So our expression can be AX equaling to B. So where this is your B, those are the variables, and this is the matrix A. So what will be the next step? After doing this, simply get A. Your A is 2, 3, 1. 3, 3, 1, 2, 4, 1. So get the inverse of A by using any of the procedures that we looked at in the last lectures. So get the inverse of A. After getting the inverse of A, then we can now solve to get the values of this x, which x corresponds to x, y, and z. So let us look at that one there. So I believe you know how to get the inverse of this matrix. So follow all those procedures very well, get the inverse of matrix, and confirm that this inverse here will be same as the inverse that I'm going to write down here. So follow the procedures very well and see how best you can be in position to obtain the inverse of that matrix I've put there. So let us look at the inverse of that matrix. Clearly we have seen our A is this. Clearly we have seen our A is this. That is the coefficient matrix for this system is this. Having written our matrix in the form AX equaling to B. So you are simply interested in this A. So get its inverse. After getting its inverse, then now we can look at how best we can solve. Now, so we are saying using the algorithm for finding the inverse of a matrix, we can easily show that A inverse is this. So follow the procedures that we did in the previous lecture and come up with this A inverse. You can use any of the above procedures of finding A inverse. Use the one that will be easier for you. You can use the one for the cofactor matrix. You can use the one where you are using the algorithm of A augmenting it together with the identity, and you row reduce this one to give us identity, then A inverse. So you can use that procedure, or else you can use the one of the determinant, 1 over determinant of that given matrix times the adjunct. But remember, the adjunct of this given matrix is same as the transpose of the what? Of the cofactor matrix. So you can use any of the procedures and show that the A inverse will be this. So hoping that you know how to get the A inverse, then let us look at how best we can obtain the values of x, y, and z. So having got your A inverse, simply now multiply. Remember we had our AX equaling to B. Your B was the constant terms. This was -1, 1, and -2. So those are the constant terms. So you will now multiply. You will now, to get the value of x, you will now multiply the A inverse. This is A inverse times the constant, the matrix of constant terms, that is B. So that matrix is this, -1, 1, and -2. So that one we can easily see it from here, from this. We can easily see it from this given point, that when you look at this, the constant term is -1, is 1 is -2. So those are the constant terms we are talking about. Now, we are looking at basically how to get the values of x, y, and z. So having got the A inverse, simply multiply it with the matrix of constant terms, which is -1, 1, and -2. You know how to multiply matrices? Multiply row by column. So this is -1 times 1. -1 times -1, it will give us +1, plus 1 times 1, it will give us 1, plus 0 times -2, which is 0. So that's why we have these two. Then next, multiply this row into this column. -1 times -1 is a 1, plus 0 times 1 is 0, plus 1 times -2 is -2. So you will have 1 minus 2, which will give you -1. Similarly, multiply this into this and be in position to get -2. So having done that, we are having our x equaling to -1 and -2. But this x here represents the variables, that was x, y, and z. So in other words, you are having x, y, and z equaling to this. So equating the corresponding terms, you can easily see that x is 2. You can easily see that y is -1. You can easily see that z is equal to -2. So from here, we now conclude that this will be our solution. But how have we obtained that? We have simply go to the coefficient matrix, which was A. We go to the inverse of this matrix. Then after we multiplied this inverse matrix together with what we call the B, that is the matrix of the constant terms. And from there, you'll be able to get what we call the solution. The same applies when you look at part B. When we look at part B of that same question, let us look at part B of the same question there. So part B of the same question was so part B is here. So part B is this. So part B still, when you look at part B, when you place it in matrix form, it will be still 2, 3, 1. It will be still 3, 3, 1. It will still be 2, 4, and 1. 2, 4, and 1. So this, you are multiplying it into x, y, and z. You are equating it to b, which b is, for this case, -4, 8, and 5. So you are having this. So this one here is in position for a. This one here is x, and this one here is the small b. So in other words, this system here is in form of ax is equal to b. So get the A inverse, get the inverse of this matrix. Then to get x, you will simply get A inverse times b. So that is what we are having. But basically we can easily see that this matrix of coefficients A is actually same as the one that we had in part A. So this one here is same as the one for part A here. Meaning that if you have already got the inverse in the first case here, then it will be the same inverse of this matrix because the coefficients are the same. What is only changing is this, and this. So these are the ones which are changing. But the coefficients for x, y, and z are remaining the same. Actually, the same applies to C as well. So after you have obtained your inverse, then you can use your same inverse to get the values of x, y, and z in part B. Same inverse to get the values of x, y, and z in part C, since the matrix of coefficients A is the same in the two cases there. Now, for that case, we can use the same matrix. For that case, we can use the same matrix. That is the same inverse matrix, since they are the same. So, from there, we shall have, simply have this. So this one here, what we are having here is the same inverse matrix here because the A is the same for part A, B, and C. So you will simply get your A inverse times B. Now your B is 4, 8, and 5. So when you multiply, you know how to multiply matrices. Multiply row by column, row by this column. You should be able to verify that when you multiply this matrix together with this, you will get this one here. And for that case, if you have your x as 4, 1, -7, then as we said, this x is simply representing x, y, and z. X, y, and z. So it is equal to 4, 1, -7. So having this, it implies that your x is 4. It implies that y is 1. It implies that z is -7. So you will go on and get the values for x, y, and z in part C. And after that, you should be able, after that, still you can easily see that our A inverse is still the same, only B is changing in part C. So you should be able to get that solution when you multiply A inverse with B. So you can use the same procedure to solve this system here, part A, part B, C, and D. So you should be able to, first of all, to arrange it in the form of AX is equal to B, get A inverse, then after getting A inverse, then get X equaling to A inverse times B. So when you are able to get A inverse, then simply multiply it with the constant terms, that is -1 and 3. You'll be able to get the values of X and Y. So you know how to get the inverse of a 2 by 2 matrix here. You know how to get the inverse of a 3 by 3 matrix here. So try that one out and you should be able to get the answer. Let us talk about this remark here. The remark says that if we have AB equaling to 0, that it does not necessarily mean that A has to be 0 or B has to be 0 or both of them. It does not necessarily mean that. For example, if you have A as 1, 1, 1, 1, and B as this one here. Let us look at the multiplication. We are multiplying A times B. So this is our A. We are multiplying it with B. So remember the multiplication. We multiply row by column. So we shall multiply this row into this column. So 1 times 1 plus 1 times -1. We have that one there. Then next we multiply this row with this column here. So it will be 1 times -1. 1 times -1 is there. Then 1 times 1. 1 times 1 is there. So we shall obtain that. So similarly, we shall multiply this together into this row. Then 1 and 1 into this row here. This column. So you must make sure that you multiply row by a column. This row multiplies into this column and again into that column. So basically when we do that, we shall be able to obtain this bracket here. So when you try to compute, this will be 1 plus -1. This will be -1 plus 1. This one down here will be 1 plus -1. This one here will be -1 plus 1. So this one here will give us a 0. This one here will give us a 0. This will be 0 and this one here will be 0. So clearly we shall obtain a 0 matrix. That is a matrix that is having zeros. And clearly we can easily see that AB is equal to 0. But we can easily see that A is not equal to 0 and B is not equal to 0. So clearly having AB equaling to 0 does not necessarily mean that A has to be equal to 0 or B has to be equal to 0. So we can easily confirm that one from that given question. So next we shall talk about some definition here, that if A is a square matrix, then the powers of A can be defined as, then we shall be denoting that A to power 0 is same as the identity matrix I, because you remember that any value or any matrix multiplied with the identity matrix, it remains the same. So instead of having, for example, a number like 8 when we are talking about matrices, then we can have this one as 8 times I, which I is now same as 8 times the identity matrix I. But I will have the order depending on the order of A that you will be considering. So if I is a 2 by 2 matrix, if I is a 2 by 2 matrix, then you expect your identity matrix or unit matrix to be like 1, 0, 0, 1. If I is a 3, if you are talking about A, which is a 3 by 3, then remember that I will be a 3 by 3 matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. So like that. So whenever we have A to power 0, we shall be putting I, which is representing the identity matrix. A to power 1 is always will be same as A. a to power 2 will be same as getting a times a to power 3 will be same as having a squared times a. Now, if you have a polynomial, for example, f of x, so if you have f of x, which is same as a naught plus a1 of x plus a2 of x squared plus up to an of x to power n. This is a polynomial in terms of x. So if we have this polynomial here, now let us consider f of a. If you are considering f of a, remember that our a is a square matrix. So whenever we have x, we shall simply substitute there a. So that is a1 of a, a2 of a squared, up to an of a to power n. However, this one here, since we are dealing with a polynomial here, just simply in terms of x, then when we place this given polynomial now to be in terms of our square matrix, then we must make sure that this constant here is also in the matrix form. So that's why we shall insert there the I. Remember, I represents the identity matrix, and this identity matrix will have the order which corresponds to the order of A. So for that case, our function will be f of A, which is a naught of I, plus a1 of A, which A is our matrix, plus a2 of A squared, plus up to an of A to power n. However, if you substitute for A and you realize that the function is now giving you 0, that you have substituted here I, you have substituted here A within your given polynomial, but it satisfies the expression that f of A is equaling to 0. Whatever you are getting here after substituting your matrix A is giving you 0 after solving and simplifying all that. So if you obtain this, then it will simply imply that A is the root or the 0 of that given polynomial. Because if you try to relate it very well with our normal polynomials, if you have f of x, which is simply x squared minus 1. So if you substitute f of 1 and you get 1 squared minus 1, which is 0. So clearly it implies that 1 is the root of this what? The root of this function or this polynomial here. So the same applies to what we call the matrices. So when you substitute within your given function or your given polynomial, and you find that whatever you are getting here is 0, then it will imply that A is the root of that given polynomial. So we can look at some few examples to understand all that we have been talking about. So let us look at this question here. We are given A, which is this, and we are given the function f of x, which is x squared minus x minus 8. Like the way we have done, we shall now have f of A to be, where there is x, we are simply inserting there A, so we shall have a squared minus a minus 8. But remember this 8 to be in matrix form, then we shall place there an identity matrix. But since we are talking about A, which is a 2 by 2 matrix, then this A must have the order which is also equal to the order of A. So for that case, you will simply substitute. So we need A squared. So you will need 2, 3, 2, 2, 3, negative 1 squared minus A. You need A here, which is 2, 2, 3 minus 1. Then again minus 8 into A, which is 2, 2, 3, and negative 1. So you need this. But it is very important that we first get A squared first. So what is A squared? Your A squared is actually same as getting 2, 2, 3, negative 1. Multiplying it again, 2, 2, 3, and negative 1. Remember that we multiply row by column. So simply get 2 times 2 plus you are having 2 times 2. That is 4. You are adding there 2 times 3. That is 6. Then next you are getting this row here. You are multiplying it into this column. So you will have 2 times 2, which is 4 again, plus 2 times -1, which is -2. So that is what we shall have. Then next we shall have this row into this column. 3 times 2 is 6. -1 times 3 is -3. You have 3 times 2, which is 6. -1 times -1, +1. So basically this will give us 10, will give us 2, will give us 3, this will give us 7. So we shall have a squared as this. So you realize where there is a squared, we shall have this matrix here, which we have obtained. So we shall have this, we are subtracting this matrix, and -8 into that. So when you do that, remember, when you are subtracting the corresponding terms. So in other words, you are getting this, you are getting 10, you are subtracting there 2, again you are subtracting there -8. Next you are having 2 minus 2, 2 minus 2. This one corresponds to this, which corresponds to that. But remember, there is 8 times this, so it will be 8, 0, 0, 8. So you have 10 minus 2 minus 8. Then the next one will be 2 minus this 2 again minus this 0. So minus 0 here. So next we do the same. 3 minus 3, then minus 0. So you have 3 minus 3 minus 0. Next you have 7. This is 7 minus minus, which is +1, then minus 8. So basically looking at this, it will give us a 0. Looking at this, it will give us a 0. This will give us a 0, and this will also give us a 0. So for that case, you are obtaining your f of a as 0. So if you obtain this, clearly we shall have to conclude that a is a root. A is a root of f of x, or else you can say a is a 0 of f of x. Next we shall look at definition, and this will be a definition of trace of a matrix. So when we consider a square matrix A, then we shall be able to define the trace of this matrix, which we shall be normally denoting by TR of A. That is, trace of A shall be denoted by that. We shall define this trace here by simply looking at the sum of the entries on the main diagonal of that given matrix. However, we shall be saying if the matrix is not a square, if the matrix is not a square, then the trace of that given matrix will be undefined. In other words, we shall be able to define the trace of a matrix, or to obtain the trace of a matrix, if we only have a square matrix. Then let us look at, for example, if you have a 3 by 3 matrix. So when you need to obtain what we call the trace of this matrix here, you simply add the elements in this main diagonal. So when you look at this main diagonal here, trace of this matrix here will be simply getting A11 plus A22 plus A33. So when you add the entries within this diagonal here, you'll be able to obtain what we call the trace of this given matrix. Then next, let us look at some few examples. For example, if we have B, which is a 4 by 4 matrix, we have our B, which is a 4 by 4 matrix, and we are interested in the trace of this matrix here. So you will simply look at what we call the main diagonal. This will be our main diagonal. So add the elements or the entries within this diagonal. So you are having -1, you are having 5, you are having 7, you are having 0. So add them, and the value obtained will be the trace of that given matrix. So for that case, we shall have -1 plus 5, which is 4 plus 7, which is 11. So the trace of matrix B, the trace of matrix B is 11. Okay. So next we shall look at another example. we look at example 2.19, which is our next example on trace of a matrix. So basically we are given A as this. Then we need to obtain the trace of A times A transpose. So it is very important that if we are interested in the trace of A times A transpose, that we first obtain this matrix here. That is A times A transpose. Then after obtaining this, we shall be able to look at the trace of this given matrix. So let us consider that we are having A as this. Then let us get A times A transpose. So our A, we are having our A as 1, 2, 0, 3, -1, and 4. What are we interested in? We want to get A times A transpose. So what is A transpose? First, A transpose will be having 1, 2, 0, then 3, -1, and 4. If you recall very well, A transpose, it means you are changing or you are interchanging rows and columns. You are interchanging rows and columns. So what were the rows will become the columns, and what were the columns will become the rows. So that is what we shall obtain. So this one here was a row, so it will become a column. This was a row, so it will become a column. So let us get A times A transpose. What will that one be? So we are having 1, 2, 0, 3, -1, 4. We want to multiply this together with 1, 2, 0, 3, -1, and 4. So clearly this is a 2 by 3, and this is a 3 by 2 matrix. So clearly the two matrices can be multiplied together. So let us look at now the multiplication. We multiply this into this. So it will be 1 times 1, which is 1, plus 2 times 2, which is 4, plus 0 times 0, which is 0. Next, it will be 1 times 3, that is 3, 2 times -1, 2 times -1, -2, 0 times 4, which is 0. Next, we shall get this. 3 times 1 is 3, plus 3 times 1, we have obtained 3, plus -1 times 2, which is -2, plus 4 times 0, which is 0. Next, we shall have 3 times 3, that is 9. -1 times -1, that is +1. Then 4 times 4, it will give us 16. So trying to compute that, we shall have 5. We shall have 3 minus 1, that is 1. That is 3 minus 2, that is 1. 3 minus 2, that is still 1. Then next we are having 9 plus 1. 9 plus 1 here. 9 plus 1 is 10, plus this one will be 10 plus 16, that is 26. So clearly, what have we obtained? We have obtained A times A transpose to be same as 5, 1, 1, 26. So what will be the trace of A times A transpose? So the trace of that will be same as simply looking at this diagonal, the main diagonal there, then you add. So that is 5 plus 26. And this will be same as 31. So we obtain the trace of A times A transpose as 31. So that's what we obtained here. So that is the answer for that question. So similarly, someone will look at A transpose times A. So look at A transpose times A and see whether the trace of that given matrix will be 31. But should be able to get that. If this is 10, you are adding there 5, you are adding there 16. So you should be able to get that. So you have to confirm that when you get A transpose times A, you are able to get this same matrix. So you will try out that and see whether it will be able to give you 31 as your answer. Let us talk about theorem 2.12. This theorem here is talking about properties of trace. So let us consider two matrices, that is A and B, that have got the same order, and they are square matrices. And let K be any scalar. Then it will easily be proved that when you take the transpose of any given matrix A, so if you have A and its transpose, then when you take trace, when you get trace of A, and you also get trace of A transpose, the two will be the same. So trace of A transpose and trace of A are equal. Similarly, trace of A plus B is also equal to trace of A plus trace of B. So if you have two square matrices A and B that have got the same order, then you can easily prove that trace of getting A plus B then will be same as taking all the sum of the individual traces, that is for A and B. Similarly, if you have K times A, you take the trace of K times A, it will be same as having K times trace of A. So like if you have trace of, for example, 2 times A, so you first obtain this, same as having 2 times the trace of A. And lastly, when you look at trace of A times B, it will be same as trace of B times A. So this one, we have already looked at that, because when you look at this one here, we are taking trace of A times A transpose, and we obtained 31. Also, when you look at the trace of A transpose times A, you realize that still it is 31. So you can easily confirm that trace of AB same as trace of BA. But let us look at the proof of one of these properties here. We shall prove this property that trace of AB is same as trace of BA. Then these other properties here, you'll be able to prove them. So you will try these other properties and see how best you can easily prove them. So let us look at proof for the part D. So we are saying to prove, we need to prove that trace of AB is same as trace of B times A. So let us look at the proof. We shall now consider AB to be C, that is the product AB same as C, and the product BA is same as D. So in other words, if we multiply A times B, we expect to get some matrix C, and when we multiply B times A, we expect to get some matrix D. But since A and B are square matrices, then we expect C to be a square matrix. Similarly, multiplying B with A will give us D, which is also a square matrix. So if they are all having the same order n, then basically let us look at the ith element. That is the I element, the ith element of matrix C. So the ith element of matrix C will be obtained. Remember, C is same as A times B. So if we are multiplying A with B, then during multiplication, remember that you multiply row by column. So it means we shall be looking at the ith row of A multiplied by ith column of this B here. So that is what we are having. Ith row of A, we are multiplying it with ith column of B. Remember, multiplication you are multiplying row by column. Every row in A, you are multiplying it with every column in this matrix B. So that is basically what we have here, that to get the ith element of C, we are simply multiplying ith row of A times ith column of B. So what will that one be? So ith row, it means we are maintaining the ith row constant. So if you are having your matrix A11, A12 up to A1n, this is A21, A22 up to A2n. So next it will be, if I consider the row which is AI, so it will be AI1, AI2 up to AI of n. So that is why we have this one here. So the same applies to the B, that is the ith column, the ith column of B. So remember, you're having like B here, B11, B12. Then I create BI somewhere there. So this is BI1. So that is the B1I. So the next it will be up to B1N. So you have that. This is B21, B22 up to B2. We are considering the ith column. So that is B2I up to B2N. So the same continues, BN1, BN2, BNI up to BNN. So you are extracting out this column here. So that is the column we are having. So you are multiplying row by column. So this will be multiplied with that. This will be multiplied with that. This will be multiplied. So we shall be able to obtain this one here. That is AI1, B1I plus up to this. So we are multiplying row by this column here. So it will be same as, so you realize that I is constant, and when you look at the B's, you realize in B also I is constant. So 1 is varying. That is 1 here, that is 1 here, 2 here, that is 2 here. So the same applies. So if we rate this now, the varying values 1, 2 up to n to be k, that so we shall have k as the summation, because we are adding summation of k equaling to 1 up to n. So we are having 1, 2, 3 up to n. So these ones are the ones varying. So where there is this, these values that are varying, that is 1, that is 2, that is n up to that one. So we shall have our k there. So similarly, when you look at B, so this is 1, this is 2, this is up to n here. So they are varying. So that is the k we are considering. So in general, you are having your summation of k equaling to 1 up to n of ai, k, then b, k of I. But what does this one mean? Because we have seen that this will be the trace of C. So if this is the trace of C, since these will be values, these are real numbers. So if you are getting 2 times 3, or you are getting 3 times 7, this is similarly same as having 7 times 3. This is same as having 3 times 2. So if I write this one here, this summation, so I can still have this one here, the summation of I equaling to 1 to n, since they are all taken from i's, since we are considering now different values of I. So it means we can now have I running from 1 up to n. Remember, we are considering an n by n matrix. So when we take i's that are varying now, they are varying from 1. When you look at this one, 1, 2 up to the last value. The last value will be an1, an2. So the last value will be n. The last value will be n. So the same applies here. The first value is 1, 2, it runs up to n. So our I will also run from 1 up to n, then k also from 1 up to n. So we are having that, the same expression still remaining. then we can now, as same like the way we have said here, that 2 times 3 is same as 3 times 2. So if I have a ik times bki, I can still write bki times a of ik. So I can still write this. But what is this value here? This value here is the value in the position for dkk, because when you look at the matrix D is the matrix which is BA. So in other words, when you say that you are having B of A, so it means you are getting BKI times this one here is AIK. So this will be the column within this, and this will be the row within B. So in other words, what you are getting here is simply the product, which we can call DKK. So with this product here is the product from B times A. And from that, we can easily realize that this one here is the trace of AB. But which trace of AB is same as the trace of B times A. So that can be easily proved.
Yeah.